This is Statistics 243 at UC Berkeley for Friday, October 24th. Okay, let's go ahead and get started. Okay, so the plan, I have a few more things to say about this linear regression problem in Spark. And then I think I'm going to defer a chunk of this until we get to optimization, because otherwise I'm going to have to introduce some optimization concepts that I'm going to have to introduce anyway. So I think I'm going to wait on that. And then what we're going to do is, after we do that for a few minutes, we'll switch over and start on the linear algebra unit. And so the idea is basically we're more than halfway through the semester. We're going to take about 2 weeks to talk about sort of practical aspects of linear algebra and computation in terms of linear algebra. We'll spend maybe a week on talking about simulation studies, simulating random numbers. And then we'll spend a couple weeks doing optimization, and then we'll have a few shorter things in the last week. But that's basically going to be it, which makes sense because as statisticians, if you considered linear algebra, optimization, and simulation, that's basically all I do on a day-to-day basis. Was one of those three things, so that works. Okay, so let's go back to this regression problem, and the idea was we have some huge design matrix of covariates x for some number n observations, and then we have p predictors or p covariates. And so the sufficient statistics here for just calculating the regression are if we can compute x transpose x and we can compute x transpose y, we can solve this system of equations simply by just taking the inverse of this and multiplying that by x transpose y. And we'll talk about what that means in terms of that we don't actually take that inverse when we get into the linear algebra unit. But if we can get it down to an x transpose x that's p by p and p is small, then basically all of our problems are solved. But if we have a big enough data set, we can't necessarily load that whole data set. We can't necessarily load this whole matrix into memory at once and do that computation. So we might need to do it in this sort of distributed fashion using something like Spark. I'll also note that if you were working on this problem on a single machine, there's no reason you couldn't write code to read in a chunk of the X matrix and compute this quantity for any given row or for a selection of rows, and you could build up X transpose X on your own. So it's not like you have to do this doing Spark. It's just, or doing a MapReduce kind of thing. It's just one way that you could do it. Okay, so I'm not going to bother to actually do this as a live demo, just because there wasn't all that much of it. So I'll just sort of walk through the code. So this code just says, suppose you give me a line that has the data for that flight in this airline data set. It's still just a line that's in sort of just text CSV kind of format. So I can split it up. I can then do some type conversions to get the y value out, which is either the departure or the arrival delay. And I can pull out, whichever particular things that I want to use as covariates. That's what I'm doing here. And I can construct xvec, which is just one row of this big matrix. Okay. And then I can compute the outer product of that x vector with itself. That's going to give me a p by p matrix. That's the contribution to x transpose x from that single observation. And I can do the same thing for multiplying the observation, the single scalar y, times the x vector for that observation. And then in this case, this is just the Python equivalent of C binding together the matrix and the vector, the x transpose x and the x transpose y, just because I want to sort of have one packaged up thing that I want to carry around. So if I go ahead and if I've got this function defined that will do this set of operations to create just this individual element and the analogous thing for xi times y, then I can do the summation as a reduction operation. So the mapping operation is to take every row, do a transformation where it's a one-to-one transformation for each row. I get back this matrix that has both of these pieces in it. So that's the map step. And then the reduction step is I want to sum across all of those results. So I want to do this summation, and I want to do the equivalent summation for x transpose y. And so that, when I do the reduction, that is then going to give me back an object that's just a simple Python NumPy object. So that's going to be an xt, xy, and then I can do the manipulations just in Python to solve this system of equations. So any questions or comments about that? Okay, and part of the thing that we were relying on was that P was not too big. If we got P to be bigger and bigger and bigger, well, I'll leave that aside for now because there's something else I want to say. But you can, as I'm talking through this next thing, think about what would happen if P gets to be too big and why this would break down. Okay, so that, it turns out, when I did that with Spark, that took about 11 minutes. So it's, not didn't take forever, but it was not the sort of thing where I pressed go and then I turned around and it was done. I had to go get some coffee in between. That's sort of the standard timing quantification of do you have enough time to go get coffee or don't you? That's whether it's quick or not. Okay, so it turns out there's a better way to do this, which is not a huge change, but is just sort of working within the context of what sort of works effectively in this kind of distributed setup, which is that if I can basically create little partitions of this matrix and block it up, and then basically do the operations to create now instead of doing it like this, it's going to be that I'm going to over partitions k, say there are from 1 up through capital K of them, I'm going to do x sub k transpose x sub k. So I'm basically going to create little blocks, and I'm going to create this cross product from this block, and then from this block, and then from this block. And then the summation over instead of summing over every single row, I'm going to sum over the contribution from each of the blocks. Okay. And so it turns out, I don't know exactly, I'm sort of not sure I can describe exactly why that is, but basically there's more overhead involved if I have to go into every line and create this cross product matrix than if I've created a block and I just do the linear algebra on the block instead of doing it individually on each of the lines. So that's what this is doing, and there's a new piece of syntax here called map partitions. So basically what I'm going to do, what I do here, and it's going to turn out this is only going to take about 3 minutes, so decent speed up from the 11 minutes, is I'm going to take the original lines, one row for every observation, and I'm going to do this map partitions function using this read point batch function that I wrote. And so what does the read point batch do? Well, it basically takes in this object that's an iterator. So the map partitions is basically going to set things up so it's going to sort of create sort of a list of lines, an iteratable object that I can then work my way through. And so the map partitions will create that iterable object that contains the lines in the first block or in any one of the blocks. And so that's going to be, then I'm going to need to take something like that as the input. I'm going to convert that to a list, and then I'm going to basically work my way through every element of that list, where there's one element per observation that's in that block. And that's what's happening when I've got this for loop going on here. And so what do? I loop through each of the lines, which is contained now in this strings list, and the ith element is one line. I have to split up. I have to do the type conversion. But I've established in advance this matrix that is going to hold this entire block of stuff for that partition or component of the problem. And so in this case, I can index into rows of that matrix just with a single set of indexing here, just because that works in Python. I can put in the x vector. In this case, it's a little bit misnamed because I've also included the y value in this thing I'm calling x vector, so that's maybe a little bit confusing. And then I can do the cross product with this NumPy syntax and then return that back. So I'm basically creating, since the y's are in here, basically for the kth block, I'm basically creating a matrix that looks like this. Here's x transpose x for the kth piece. Here's xk times y. Here's the transpose of that. And then here's y transpose y, which I guess I'm not actually going to need, and I have sort of some duplication here, but I'm going to need this piece, and I'm going to need that piece. So now what I can do to create my sum over all the blocks is I can take the result of doing this mapping to the partitions that gives me this matrix, one per partition, and then I can do the reduction on that to do the summation over k instead of doing the summation over I. And when I've been experimenting with all this, including in some of the model in some of the other model fitting, basically creating these chunks and operating on chunks seems to empirically be rather more efficient than working through things line by individual line. And then here's just the example of what I would actually do to get the least squares estimator or the MLE. Their equivalent is I'm taking this upper block here. Well, I'm taking the analogous quantity once I've done the summation, so the k's are no longer here. I guess there was a k there that I didn't write. And now I'm just pulling out that upper left-hand block here, and I'm pulling out the right-hand vector there, and then I'm just solving the system of equations to get the beta hats. Okay. So any questions about that? Yeah, Guang.
How does the iterator know to jump by p?
Yeah, that's a good question. I'm not jumping by p. I'm jumping by the size of the block.
Okay.
So here that's why I have to do what's the length of strings of STRS here. Because that's going to come in as this iterable object that's going to contain, there's going to be the original, running out of space here, there's going to be the original lines object, which just has the 1 up through n lines. The read map partitions, which is now off the board, is basically going to break things up into chunks of lines. And that's going to come into this function as the input object, where I can operate it on it in this fashion. I can convert it to a list, and then I can say how many rows are in the list, basically.
So the iterator is a block coming in?
Yeah, I guess I'm sort of being loose with my terminology. It's coming in as something that I can manipulate in this fashion. It's basically, so let's see. So let's think about this a little bit more. So it is, we're taking a partition, which is basically a set of lines, and then we're applying a map operator to that partition, and this, I'm not sure exactly sort of what form this iterator is in, except I know I can convert it. It's in this form that I can convert to a list, and then I can loop my way through the rows of the list, basically. So yeah, I don't have a deeper understanding of what that structure actually looks like, but we can operate on it in this fashion.
And is that because up above you reduce it into 192 blocks?
Yeah, so that's part of the magic here, is if I just had this as, originally when I was reading in just the 3 airline data files for 1987, 88, and 89, I would have only had 3 partitions, and this probably wouldn't have worked nearly as well. And in fact, it's possible that it might not, that any one of those partitions might not have all fit in memory on whichever node it happened to be on. So that's sort of going to depend on how big the data set size is, how much memory you have on each node, how the partitions are sort of blocked, how they're allocated across the different nodes. So yeah, so that initial repartitioning generically that initial repartitioning would be important here. Other questions? Okay, so I'm not going to go into this next bit. I'll wait for that until we're on the optimization unit. But let's just explore why I even have it here, which is what happens as p gets large. So I come along, I say, hey, this is great. I have 120 million observations in the airline data set. I could fit a regression model that has 50,000 predictors in that model because I have so many observations. I have enough statistical power to actually be able to estimate that many coefficients, right? And with that big a data set, there might be a lot of complexity to it, and maybe I want to sort of capture a lot of variation by having a lot of these predictors in there. Okay, so how would that cause what I've done here with the X transpose X and the X transpose Y kind of approach to break down? Yep.
If you're doing these huge matrix multiplies, it's really slow sometimes, or?
Yeah, so part of it is that some of these calculations will definitely slow down. So there's something else. There's another aspect to it that even though it might take a while, we might be willing to wait. Yeah.
It's like cross product, so you're like gonna run out of anyway.
Yeah, I'm now going to be building up these cross product pieces. Let's say we've got it in blocks here. These individual components. Each of these is now going to be a p by p matrix. If that's 50,000 by 50,000. I'm not going to be able to do that in my head, but we could take 50,000 multiplied by 50,000 multiplied by 8 for 8 bytes per double value, and then we can figure out how many gigabytes that is. I think it's something like 20 gigabytes or 40 gigabytes or something like that. So it gets to be this really big object. All of a sudden, we can no longer store that thing in memory in this paradigm that we've been using, and it's going to have to start writing to disk. If we get p even larger and larger, we might not even be able to store that thing on disk eventually. So we would very quickly run into basically either memory or storage limitations. In addition to it, would probably be fairly slow to do. So basically, what I talk about here is, even though in principle mathematically we can do X transpose X, we can do X transpose Y, we can solve this system of equations, it's going to be too big a computational burden for these reasons that we just discussed. And so instead, what I might choose to do is to treat this as an optimization problem where I pretend as if I don't actually know what mathematically, analytically, I know what the answer is. It's X transpose X inverse times X transpose Y. But if I pretend that I don't know that that's the solution or that I can't use that solution, I can just think of this as an optimization problem. I'm trying to minimize the sum of squares between Y and X beta. So I'm trying to minimize that. I guess I've got sort of bad notation because this is a vector, so in matrix vector notation. So if I start out with some initial value beta, this is just going to be one-dimensional optimization, but really we're going to be working in this p-dimensional space. So I start out here, and I can do gradient descent. I can find the gradient with respect to I can find the gradient of the objective function with respect to beta. I can travel downhill once I know that gradient vector, and I can basically work my way down to the solution. And this is this is going to be suboptimal in the sense that I'm doing this iteratively when I actually know the mathematical form of the solution. But it doesn't require me to do all this matrix stuff. All I need to do is calculate the gradient, which is just a vector, one for every element of the beta vector. So even if p were 50,000, 50,000 is not all that long a vector. I can calculate a gradient that has 50,000 elements in it, or for that matter, 1,000,000 elements in it, and I could try and solve the optimization problem this way. So that's basically what I talk about here. Either calculating the gradient of all of the betas at once of the whole vector, or individually updating one of the betas, then moving on and updating the next beta, which is called coordinate descent. We're going to see all this in sort of gory detail in the optimization unit, so I think I'm going to leave it at that. But hopefully that sort of puts some of this in context and gives a little bit of looking ahead to where we're going to be going eventually. Okay, questions or comments? Okay, so let's switch over to Unit 11. Recall that Unit 10 was the Python material. So here we are. I asked you guys to look at and read the first 5 pages in advance, and they're basically just sort of background linear algebra material that has linear algebra facts and results that we're going to rely on when we're covering the rest of the unit. Okay, so let me just say another few sort of prefacing words here, which is we're still going to use a bit of R here. but it's just going to be basically as illustration. We're mainly going to be thinking about numerical issues in doing linear algebra. And it's going to be very practically focused. Like, we're not going to be doing, I'll show you a couple proofs, I guess, but not in a lot of gory detail. And the main idea that we want to get out of this is how do we actually implement linear algebra on a computer in a way that it will work and it will be efficient. And also, sort of a side goal here is, and we'll see some of this today, is to be thinking about linear algebra from a statistical perspective and trying to interpret some of what we're doing when we do linear algebra calculations statistically. So I don't know about you guys. When I took linear algebra, it was even before I knew that I was going to become a statistician, and to me it was just this very dry topic that had no bearing on in reality, right? So hopefully what we'll see here is that a lot of the sorts of things that you've seen in linear algebra have statistical interpretations, and hopefully that will make it more interesting and more grounded. Okay, what else did I want to say as preface? Oh, the other thing to note here, and we'll see this I guess a little bit later in the unit, is even though we're going to be doing linear algebra quote unquote in R, as I think I've mentioned before, all of the linear algebra is being done either by the BLAS library that R is calling, which is the basic linear algebra subroutines that do matrix vector and matrix calculations like matrix vector multiplication and matrix multiplication, or LAPACK, which is the linear algebra package, which will do sort of the higher level linear algebra type stuff, like doing matrix factorizations, like getting eigenvalues and eigenvectors, doing an SVD, doing a QR decomposition, doing a Cholesky decomposition, things like that. So in some sense, it's not really R doing it, it's R just passing along the calculation. And that would be the same if we were doing this in Python or in MATLAB as well. Okay, let's see. So you guys have looked at this before. In terms of what the goals are here, we're gonna see some of the business that we've saw in Unit 7 in terms of computer arithmetic come back into play when we're talking about linear algebra. And I'll just highlight this since I put it in bold, so it seems worthwhile highlighting, which is we're going to have to sort of think in two different ways. We can think about what the mathematical expression we want to evaluate is, but in many cases, when we implement that on a computer, it's good to know what that is, and we want to keep that in mind, but we're not actually going to explicitly, operation by operation, do explicitly what we said was in the mathematical operation. We're going to often rewrite the calculation in a different way that is either more efficient computationally or it is better behaved from the perspective of the fact that on computers we can't store numbers with infinite precision. Okay, and then just a review here, just to keep, this is one fact that's always good to just have sort of ready at hand in our brains. If I have an n by n matrix and an n by n vector, do I have a name for my matrix and vector AB? So suppose both of these are n by n, or suppose I have an n by n A and I'm multiplying it by an n by 1 matrix or vector, whatever you want to call it, in this case B. How many calculations do I have to do this calculation and to do this calculation? Florian? Yep. So this is n cubed, right? We're thinking of, we have columns and rows. Every time I multiply a row and a column, these have n elements in them, so there's going to be n multiplications I have to do, and I'm going to have to sum across all those n elements, so there's also going to be n additions, or maybe n minus 1 additions. So each one of these is n calculations. I have to do it for every column, so that's n squared. I then have to do that same thing for every row, so that's n cubed. So this is, I mean, in some sense this is exactly n cubed, but in general we're going to be saying what's the order of the calculation, so this is order of n cubed. And what about this? N squared. All right, so whenever you think matrix multiplication, think n cubed. Whenever you see matrix vector multiplication, think n squared. The other way to think about it that I think is helpful is if I have to write this on a computer as a for loop, I have to write 3 for loops to do that. If I have to write this on a computer in for loops, I have to do 2 for loops, and so the 2 and the 3 sort of go with the order of the calculation. And what we'll see is basically any time we do a matrix factorization, like if we take a matrix that's n by n and we get a Cholesky decomposition, we do a QR decomposition, we do an SVD, we do an A decomposition, all of those are also going to be order n cubed. So they're basically essentially equivalently as expensive as just multiplying 2 matrices together. Okay. So that's all I want to say there. You guys have looked through that, so there's sort of some more details in there about constants that go in front here, but I just wanted to remind us all of that. Okay. All right, so were there any questions people wanted to ask from having looked over this? Okay. And we're happy to take questions in office hours, or if you want to ask afterwards, that's fine. But we are going to rely on all of these, for the not maybe on all of them, but most of these results. I've already asked you guys this question. How would I do this problem? I forget if that came up in the section when we were talking about efficient calculations in R. Does anybody remember? No, maybe we didn't do it. All right, so let's talk about this. So suppose I want to find the trace of a matrix, but the matrix is the matrix that I'm trying to find the trace of is actually the result of having done a matrix multiplication. So I'm having to do this. I'm creating, so this new vector that's the product, and then I'm doing the trace, so I'm trying to sum the diagonal elements. So if I have to do this matrix multiplication, n cubed calculations, right? So if n is any decent size, this thing grows, the number of calculations that have to be done grows quickly. Okay, so why don't you take 15 seconds, 30 seconds, consult with your neighbors. How could I do this calculation without actually having to incur that n cubed cost? Did you have a... What's that? Yeah. Well, no, don't answer yet. I want to ask. I want to let people think about it. Okay, so take 20 seconds. Think about what you might do to solve this problem without doing the matrix multiplication. All right, so Aurelian already pointed out one thing which I wanted to highlight, which is, and I think this is a good principle to think about. If I look at the result and what I'm doing, the calculation I need to do at the end only involves these elements. So any calculation that I've done to put numbers in here is wasted calculation. So if you see other kinds of problems where you see that kind of feature to it, it's a good hint that you should think about what are the calculations you're doing to get there, and is there some more efficient way to do it. So how can I get this element here? Okay, I just need to multiply this guy times that guy, right? And how can I get this guy? Just need to multiply the second column times the second row, and so on and so forth. So, okay, I suppose I could do that with a for loop, but how could I do that in R even more efficiently than that?
Cross product.
Let's see. No, I don't want to do the cross product because that's basically going to compute this whole thing. Yeah, really.
You can turn one matrix into another long vector.
Okay.
And the matrix into a long vector, and you just multiply.
Okay, so I could turn these things into vectors, but I need to turn it into vectors in such a way that the elements match up correctly, right? Okay.
What if you took the trace of the second matrix and then just multiply the two matrices by each other together, not doing matrix multiplication, and then
Just doing the direct multiplication?
Yeah.
Yeah. So I think Aurelian's solution would definitely work, but it would involve us sort of thinking through how to make sure we got the sort of things put into the vector correctly. So I think this one's going to be a little bit easier, which is take the transpose of this. That's now going to convert this into sort of pictorially, hopefully you can follow what I'm doing here. Now we've got two matrices where I just need to multiply this times this times this times this. If I just do A star B, that's what R does. It's vectorized, so it's just going to do it. And in some way, actually, that what we've done here by doing this is R is essentially just treating these things as vectors. So it really is doing a Aurelian's solution to this, but in a way that sort of, we see that it's sort of using R's vectorization. Okay, so we get that, and then we just sum the result up. We actually don't even need to do the row sums because the trace is summing up all these elements. So we just need to do this and then just do the straight sum of all those guys. Okay, so now what I'm going to do for the rest of class is I want to talk about some of these concepts in linear algebra from the statistical perspective. And so this is basically just going to be sort of math and statistics without really much computing to it. So let's see, where am I here? Okay, so the first thing I want to talk about is this idea of linear independence and rank and basis vectors. So, and some of you, I'm sure you guys, at least some of you or many of you have seen this before, but I think it's nice to see it again as we start to think about linear algebra. Which is basically when we have linearly independent vectors, we're often thinking of this in the context of a regression problem. So we've got some matrix X that has columns, and we have P covariates or predictors, and we have N observations. And we're basically thinking about taking these columns, and one way to think about it is taking these columns and operating on them. So I can think of regression as being basically, I'm going to express my vector y of observations as the first column of x times beta 1 plus the second column of x times beta 2 plus so on and so forth, and then I'll have my vector of residuals. So what is this? This is just taking the regression fit part of this, leaving out the residuals. Is just taking a linear combination of these columns of the X matrix, which you can think of as just basis vectors. They're just patterns on that we're trying to use to explain the observations. So we take linear combinations of those patterns, and that gives us our predictor, and then that differs from the actual observations by whatever the residual is. Okay, and as you guys have all seen, if I have that one of these columns is just another column but multiplied by some scalar value, or that one of the columns could be represented as a linear combination of some of the other columns, I'm not going to be able to get the regression estimators because of the fact that I have this collinearity, this complete collinearity between some of the columns of the matrix. And another way of expressing that is that these columns are not all linearly independent vectors. Okay, so what I need to have is that they're all linearly independent. Which doesn't mean they're orthogonal. They could have some variation basically in the same direction, but it means you can't explain one of the columns just completely with the other columns. So you can't have any redundancies in there basically. And so if we think about the rank, how rank relates to this, since the rank of a matrix is the number of linearly independent rows or columns and is at most the minimum of those two things, the rank of this X matrix is going to be at most P. Okay? And if we have this case where any of the columns of the X matrix are linearly dependent on the other columns, then I have that basically the number of effective basis vectors that I have to explain the result is less than P. So I think in here I was maybe saying that Q was less than P in that case. So Q I'm using in the notes as the number of linearly independent vectors in X. So let me say a little bit more about sort of basis vectors and projections. And I'll just do this in sort of low dimension, and hopefully we can see some of the intuition for higher dimensions, although sometimes that gets hard to do. Okay, so obviously if we're in 2 dimensions and we're thinking of explaining any given vector, we can just explain that as how far out are we in the x direction, and how far are we out in the y direction? So we can say, okay, I can explain this guy as c1 times the vector 1, 0, plus c2 times the vector 0, 1. But there's sort of nothing magical about the axis-oriented directions. Like I could do a rotation here, and I could also express this vector, which I've sort of inconveniently put right on the diagonal there, so I'll move it off a little bit. I could rotate my dimensions, and I could have a new set of directions that are here, and I can still express that same vector here. I can still express this as a linear combination of these basis vectors, even though I've rotated them. And in fact, there's nothing about the orthogonality that's even particularly crucial here. I could instead say, start over again. Let's suppose I have the vector I'm trying to explain here, and I have this vector, and I have some other vector here. I can explain this guy as a linear combination of these two vectors as well. And I have to do a little bit of business with inner products and normalizing vectors to figure out what the coefficients are that would explain this vector as c1 times, in place of the 0, 1, c1 times this vector plus c2 times that vector. But basically that's all we're doing when we're thinking about linear regression, is we're taking the columns of the X matrix, we're thinking of them as these vectors, and then we're trying to explain the Y vector in terms of linear combinations of those columns of the X matrix. And you can see how this would how this issue of the linearly independent vectors would break down here, which is if instead of having two vectors that are linearly independent, I just took this vector and scaled it so I had sort of another copy of that vector, but here, that's then not going to be very helpful in terms of explaining these guys in terms of being able to exactly explain this vector. Although we could still project this guy into this guy, so maybe my analogy is breaking down a little bit here. But, okay, so questions or comments so far? Okay, so where am I here? Okay, so I basically already said this. If we, what will happen if we have one or more columns that are linearly dependent on the other columns is when we go to compute X transpose X, we'll end up with an eigenvector of this matrix. Or we'll end up with an eigenvalue of this matrix that is 0, one or more that are 0. So the number of 0 eigenvalues will be equal to p minus q. So q of them, which correspond to the linearly independent columns, will have positive eigenvalues, but the remainder of them will have eigenvalues that are 0. And what that means is we're not going to be able to do X transpose X inverse because of the fact that we have the 0 eigenvalues in there. Let's see. So okay, I guess the other thing I wanted to mention here was to think about what happens as n, how does the size of n relate to q? So if we have n bigger than q, then that's the usual regression context, right? We're trying to explain n observations with many or somewhat fewer covariates than we have observations. And so that ends up involving a projection that I'll say a couple words about in a minute. If we have n equals to q, then we can basically fully explain all of the variation y with the covariance, right? So the way that I think about this, because it's hard to think in high dimensions, is suppose q is 2 and n is 2. I have two observations. I can directly fit a straight line to those observations, and there's no variation left over. So there's no residual. And if I have n less than q, then again in my simplistic picture, suppose I have n equals 1 and q equals 2. Well, then I have the case that I just have a single observation, and any regression line could perfectly well explain this, right? This one works, this one works, this one works, that one works, et cetera, et cetera. So when I try and think about this stuff as like what happens if when I get to higher dimensions, I often end up sort of going back to the situation, okay, well, here it was fitting a line. As q gets bigger, I'm thinking of fitting some sort of hyperplane to these observations, but the same thing happens is I can fit a hyperplane where all the observations are sitting on that hyperplane if these two things are the same. And then the way that I tend to think about this may or may not be helpful, is again, let's think about, now let's think about q being 2 and n being 3, and think about what happens when we're doing a projection. If I think about the columns of the X matrix, one of them I can think about as this line that sort of goes along the bottom here, and for the sake of simplicity, let's assume the other one's orthogonal, and it's a line going along the floor here. So now I want to explain some vector y, but my vector y, if I have n equals 3, my vector y lives in 3-dimensional space, so it's sort of sitting up here somewhere. And if I want to try and get the best explanation for y that I can, using the basis vector that's going along the floor there and the basis vector that's going along the floor here, I'm basically going to do a projection. I'm going to drop this point y down onto the floor to the closest point on the floor, and that's going to be my predictor x beta. It's just going to be a linear combination of these two basis vectors that are on the floor. And if the basis vectors weren't orthogonal, maybe one of them would be here and the other one would be on this line that I'm walking on right now. But those two vectors, either the orthogonal ones or the one going here and the one going here, I can take linear combinations of either of those two vectors and they will basically fill up the entire floor. So either of those two vectors span this 2-dimensional space, which is the entire floor, because I can explain any point on the floor as either a linear combination of these two vectors or as a linear combination of those two vectors. Okay, so that was hopefully giving a little bit of sort of intuition for what's going on here. Any questions or comments? Okay, so I wanted to say, I just mentioned a little bit about invertibility in terms of X transpose X. I want to say a little bit more about this. So I wanted to try and relate some of these linear algebra terms and concepts that come up all the time if you're taking a linear algebra course, and see sort of how some of them relate to each other and how they relate to statistical ideas. So that's what I tried to do up here with this thing that I'm calling equivalences. So the idea is, if I have a matrix A that's positive definite, so I have some square symmetric matrix A. If it's positive definite, what does that mean? It means that we can also think of it as a covariance matrix. Those two things are equivalent. And what does it mean for something to be a covariance matrix? It means that for any x that's not 0, 0, x transpose AX is bigger than 0. Well, what is x transpose AX? If y is bring my own erasers now. I have one everywhere I was. If the covariance of if I have random variable y, random vector y, and the covariance of y is a, then I can think of the covariance of x transpose y. So this is random. This is just a fixed vector x that has some values in it. So what is this? This is just basically a linear combination of the values in y. And what's that covariance? In terms of if I want to bring A in here. I was in the class. I was in 201A on the day that you guys were talking about this, so I know you guys were in 201A know the answer to this. X transpose A X. Right. because it's x transpose times the covariance of y, which is a times x. So what does this mean? What is that? Where does the x transpose ax come from, just in terms of motivating it? It comes from thinking about covariances of linear combinations, and so basically it comes to the idea of the covariance matrix is that it tells us what the variation of linear combinations of the random variables in y are. Okay, so there's this business about covariance matrices, but what does positive definiteness means also that the eigenvalues, which is what I'm denoting as the lambda i's are all bigger than 0. And if that's the case, then this is not an if and only if, but it goes this way, then the determinant of A is bigger than 0. That also implies that A is invertible, and then all these things are equivalent, that A is full rank, and A is just, we say that also that A is non-singular. So one way of let's see, what else do I want to say about this? So if I do have x transpose x from a regression problem, and I have that n is bigger than p, and I have that I don't have any linearly dependent columns, then I have x transpose x as a p by p matrix, and it will have all of these properties. In particular, that we can invert it, that it's full rank, it's non-singular, the determinant's bigger than 0, the eigenvalues are all in this case going to be bigger than 0 as well. And we aren't going to have any problems doing the regression in that case. And the other term that we'll see some is cases where A is positive semi-definite. And that basically corresponds to the case where, in some case, where we have some zeros in here and we have one or more 0 eigenvalues. And that's the case where where we have a determinant that's 0 and we're not going to be able to invert A, and it's not going to be full rank, it's going to be a singular matrix. And what we'll see next time is we can think about that as being a covariance matrix where there's one or more constraints built into the covariance matrix. Because we can think of the lambdas, and we'll see this more next time, we can think of the lambdas as basically variances of particular linear combinations. And so by having a lambda that's 0, it's saying there's some linear combination that has a variance of 0. And that basically, when it has a variance of 0, that basically corresponds to a constraint. So we will, where are we in terms of time? Yeah, so we will get back to that next time. Oh, the other, just as an announcement, I put this on, I put an announcement on Piazza, but I realized there were a few things that I needed to tweak in terms of the instructions for dealing with the cloud instances and a few more hints for that. So go ahead and look at that announcement and the new information in the how-tos files. And I will see you on Monday.